Hello, everyone. Welcome to this week's Green Bank Observatory Community Zoom. I'm Jim Jackson. It's a pleasure to be back. I've been gone for a while. I've been on medical leave. So I had a tumor in my mouth and I had some surgery that all went very well. It was removed, and then I had some treatment for radiation and chemotherapy. And I am happy to say that I am well recovered and resuming my duties here at Green Bank. I've missed everyone. I've missed the observatory, and it's a real pleasure to come back. I want to thank very much David Freyer for stepping in as interim director. David did a fantastic job. I was very pleased to know that he was in charge and doing some heroic work. In addition to his normal duties, he took on the director's role. So I am just very grateful to David for his hard work and appreciate all you've done, David. Just a couple of quick announcements before we begin. We begin our summer maintenance May 6th, so that's coming right up. Maintenance this year will be we're working on the foundation and the grout, so there'll be a lot of work shoring up the telescope. So the time allocation committee has met and reviewed Green Bank proposals. Those disposition letters will also go out the week of May 6th. So the committee has met, and now we're just making sure we can schedule everything, and we will send out those results just as soon as we can. Some of you may have heard things about the NSF astronomy budget, and there is a cut in the NSF astronomy budget. We're not sure how that cut will affect Green Bank. Early indications are not badly, or not as badly as perhaps it could be. We don't know the exact budget yet, but I will, as soon as we do, I'll let you know. I'm optimistic that we'll at least be flat funded. So I think that's kind of the indications we're getting, but nothing is set in stone yet. And the NSF has to make an official determination. Once they do, I will let you know in this venue. So that's all I have for the observatory announcements, and I'll hand it over to Jay Lockman to introduce today's speaker. Jay.
Thanks very much, Jim. Today's speaker is Karen O'Neill from the Green Bank Observatory, and she is speaking about a galaxy without stars. And let me just remind everyone that this is being recorded for future viewing. And if you have questions, please submit it through the Q&A button on the bottom, and we will get to questions at the end of Karen's presentation. Take it away, Karen.
All right, thanks, Jay. I appreciate it. And thanks for the chance to talk about this. So today I'm going to be talking about newly discovered galaxy, GEO 613 plus 52 for its very original name. And I should say that this is work being done by myself as well as my collaborators, Wim van Driel with the Observatoire de Paris and Stephen Schneider at the University of Massachusetts. So before I get into this, just to make sure we're all sitting on the same page, I want to talk for a moment about low surface brightness galaxies. I suspect this will be old news to a lot of you guys, but again, just to make sure we're all kind of sitting on the same page when I start to talk about the new discovery. So what's a low surface brightness galaxy? Pretty simple. It's just a galaxy whose central surface brightness is at least one magnitude fainter than the night sky. And low surface brightness galaxies morphologically go everything from the beautiful spiral galaxies like you see on your left with Malin 1 to pretty amorphous blobs like you see on the right with PO2-4. Thinking about the colors of these objects, the colors again trend from blue to red, just like every other galaxy, but they do tend to trend towards the blue. So the average low surface brightness galaxy is a bit bluer than its spiral galaxy counterpart. Looking at the gas content of the average low surface brightness galaxy, again, low surface brightness galaxies tend to be gas rich when you're talking about neutral hydrogen. So you can kind of see that in this plot to the right, where you've got decreasing surface brightness going to your left along the x-axis, and then an increase in gas to light ratio, luminosity ratio, going up the axis. So you can see that there's a trend towards higher gas mass to lower surface brightness. Looking at other gases, you can talk about the molecular gas content of low surface brightness galaxies. Now, this is a harder topic to talk about simply because there haven't been a lot of detections. There's been a lot of measurements, a lot of non-detections, but fewer detections. But again, the molecular gas content through both measuring the CO gas or looking at other indicators show that on average, the low surface brightness galaxies have lower molecular gas content than their higher surface brightness counterpart, on average. Again, there are always exceptions. There are galaxies with a good bit of CO gas, particularly in the center. But if you look at the disks, on average, it's a lower molecular gas content. And then finally, low surface brightness galaxies, again, on average, seemingly have a high dark matter content. And you can see this from, these are some fairly old plots from Erwin de Block and Stacy McGaugh. I think I flipped their names on accident, which just kind of shows the short dashed lines are the contribution from the halo to the total mass, and that the contributions from the halo, from the dark matter, are pretty high. And, you know, as time has gone on, we've been able to change this a bit, but nonetheless, it doesn't change the fact that on average, low surface brightness galaxies appear to have a higher dark matter content than their high surface brightness counterparts. So finally, last bit on this little background are ultra diffuse galaxies. This is a topic you see in papers fairly commonly now. And ultra diffuse galaxies are just a subset of low surface brightness galaxies, which are, as you can guess, far more diffuse than the low surface brightness galaxy of 20 to 30 years ago. And this is just, they're being discovered as instrumentation is able to push to lower and lower surface brightnesses. And so they are the lower surface brightness counterpart, and as you'll see a little bit later, typically have a slightly smaller total mass or dynamical mass than some of the other low surface brightness galaxies. So we'll go back to that. All right. So finally, let me move on to the topic of the day that I'm actually supposed to be talking about, and that is the discovery of this new galaxy. So this came about as part of a new survey that we did, looking at known low surface brightness galaxies that came from a variety of different optical catalogs. And we wanted to go and just measure the neutral hydrogen gas, dynamical mass, and redshift of these objects, redshift when it wasn't known. So to do this, we used 3 different telescopes. We used the GBT here in Green Bank, we used the Nancy telescope in France, and we used the Arecibo telescope in Puerto Rico. And for the most part, to be efficient, each telescope had their own set of objects to look at, but we also overlapped a number of objects between the different telescopes just to make sure that our data reduction, calibration routines, all of that made sense and evenly aligned with each other. So in writing up all these catalogs and writing up the results, we found that for one source, there was a real discrepancy between what the GBT was saying and what Nancy was saying. And this wasn't just a discrepancy in terms of signal to noise and intensity, but it was actually a discrepancy as well in velocity space. The Nancy telescope was indicating a velocity of around 10,000 kilometers per second. GBT results were more like 5,800. That's not something you can explain away very easily. So after an embarrassingly long amount of time on my part of trying to understand why this happened, I finally went and looked into the catalogs and discovered that in the GBT catalog on one source, and only one source, I had mistyped the declination for this. But nonetheless, there was a source there, so that was pretty cool. The assumption was at this point that the source that we had found was a known galaxy, and we just happened to get an H1 observation of it. So we figured we'd be able to at least publish this as, hey, we did this on accident, but here's the H1 profile of this galaxy. So we were quite surprised when we went into various catalogs, Sinbad and CDS and NED and all those groups, and started to look for an object and found that there was no known object around this to a pretty big distance. So nothing between us and the detection, and then go another about 100 megaparsecs out, nothing there. And then in two-dimensional space, if you just draw a ring around this galaxy, again, there was no cataloged object within about 100 megaparsecs of the source. So that was pretty surprising and pretty unexpected. And we then decided, all right, well, if it's not known, there's got to be something there. We just need to go and find it. So we went to search for archival optical data of this area of the sky. And unfortunately, in doing so, we found that this is just not a popular sky area for optical catalogs, and so that means there wasn't a lot of deep imaging there. So the deepest image we could get was the Sloan Digital Sky Survey, which still takes us down to a surface brightness limit of about 25 in the G filter, so still pretty good. And this is what the SDSS image looks like here. I've just co-added 3 different filters to try to get a little bit deeper and a better image of the sky. So now let's put on top of that image the GBT observations. So let me step through these observations for a minute here. So what you're seeing in this image, what I've overlaid on top of the image, the circles are the GBT beams. That's a 9.8 arc minute GBT beam on the sky. Then the white circles are all of the locations where the GBT did not detect any neutral hydrogen. The colored circles are where neutral hydrogen was detected. Now, the actual color of the circle is simply reflecting the offset of the central velocity found within that neutral hydrogen profile compared to the average velocity, radial velocity for all of the profiles found. And then the thickness represents the intensity. So it's a lot of information at once. Let me try to show it to you in a slightly different way. So you can see this idea again, only now what we've got is I'm showing you the actual H1 profiles from those individual observations, where we flipped the non-detections are now black on white instead of white on black, but then all of the other colors line up. So again, you can take a look at this and see that, for example, the darkest blue on the bottom left is also where we saw the most intensity, so it has the thickest lines on there. So these are the observations we were able to get with this, and we can zoom in on them again to go and try to look for a source within these detections, and the answer is there's nothing. If you look very closely in this image, there are a couple galaxies in there. There's one, probably the biggest is to the bottom left of the blue circle there, but all of those are known objects with known velocities, and all of those are velocities that are well away from the detected velocity of the source. So again, that 100 megaparsec-ish sphere around us where we couldn't detect anything. So there's truly nothing there. All right, so now let me tell you a little bit about what we did detect, what we do know about this object. And so these are the measurements we were able to discern so far about the object itself. So the top row are the measurements we were able to make from the H1 spectra that we got. And then the bottom is the measurements we were able to, the lower limits we could set based off of the Sloan Digital Sky Survey data that we have. So take a minute here and let's look at these 3 numbers. So that's the total gas mass we have, W20, which is your velocity width, or you can also think of it as your total dynamical mass within the system. And then again, the surface brightness limit that we have right now. So we can plot that up on our plot, and so here again you see those same numbers. Your vertical axis now is again your central surface brightness, and I should note that this is only looking at low surface brightness objects. A normal spiral galaxy would sit down below this chart. And then on your x-axis are our measurable quantities, so you've got your total gas mass on the left and you've got your velocity width on the right. Then the nice big bright star is our object. Yay, that's the fun thing we're looking at. I should note that I've put an arrow on the object to indicate both that going up the vertical axis, we only know a lower limit, and so clearly it is the central surface brightness of this object must be fainter than what we were able to go to, because we don't see anything yet. But it also has the potential to go to the right in both plots a little bit. So right now, if you go back to the plots I showed you earlier, you can see that seemingly we detected this object, and it looks like, if you just take a look at this, it could be an extended source, and it might be. But the reality is we don't know exactly where on this plot the center of the galaxy lies. And because we don't know exactly where on this plot the center of the galaxy lies, we can make some guesses, but we don't know. We don't know whether or not, for example, that red circle to the top left is an actual detection of extended gas from the galaxy, or if we're detecting a little bit of the center part of the galaxy in the side lobe. And so because of that, we can't really state yet what the extent of this galaxy is in H1. And so that leads us to, come back to this plot, not be able to conclude for sure if we have fully detected all of the gas mass in a single beam, or if perhaps there's a little bit more gas extending outside the GBT beam. And similarly, we have an issue with knowing the actual total velocity width for the same reason. So that's why there's arrows on these plots. Okay, so let's get into the fun stuff now. So again, the red star is our new source. Then plotted on top of that are the detections with the alfalfa survey. That was the Arecibo all-sky survey, all Arecibo sky survey that was done to a fairly good depth. We thought those would be similar objects, and so we thought they would be a good comparison. And then on top of those, in the blue triangles, the upside down triangles, I should say, are a number of other sources not necessarily found with alfalfa, but that have come out lately as extremely ultra diffuse galaxies, if you can say such a thing, or almost dark galaxies. And the most interesting of those are the two at the top, AGC 229101 and the Noob galaxy. Both of these are fairly recent publications of sources, and both of these are actually showing you objects that we thought were going to be very, very similar to our detected source. And what you can see is on the left, when you're just looking at the total gas mass, you can imagine that our new detection is very similar to something like AGC 22901. And why can you guess that? Because, if you just move it up a little bit in central surface brightness, it looks like the total gas mass is pretty similar. So that's exciting. But when you look to the right, what you really get a good view of this source. And when you look to the right, what you're looking at again is the velocity width, but you can think of that as your total dynamical mass captured within the GBT beam. And so you can see, as I mentioned at the beginning of this talk, that both AGC 229101 and Noob have a total velocity with a total dynamical mass that is significantly less than what we're seeing for our new detection. And so in other words, our new detection really is something new. It's something different than has been seen before. And that's shown by the fact that it has a dynamical mass similar to that of a typical spiral galaxy. Oops. All right, so what have we found here? So again, we've got a low surface brightness galaxy, a dark galaxy or a close to dark galaxy. We've got a galaxy that is fairly isolated and undisturbed. And we've got a galaxy whose gas and dynamical mass is similar to that for a normal high surface brightness spiral galaxy. So what does that lead us to? It leads to the obvious question. Why the heck is this thing so unevolved? What's going on with this? The answer can't be given quite yet. We can't say for sure because, of course, there's a lot more measurements to do. But here's my best guess of what's going on. So you've got an object who, from the early ages of the universe, the gas itself was just too diffuse for ready star formation. But unlike what happens in most of the universe, it also didn't have any nearby companions. No other galaxies nearby to spur star formation through interactions, tear the galaxy apart, to fly nearby and cause a central coalescence of the gas or anything like that. So in other words, we have what you could think of as kind of a nearby primordial galaxy. That is, we have a galaxy which, due to the lack of nearby neighbors, formed in the early universe in a very low density regime, and simply has nothing to spur that big bright star formation that you get in most other galaxies. So nothing to give it something that has currently detectable visible light. All right, so that's cool, that's exciting. And then you can ask the big question is it unique? Is this the only one of these things out there? The answer to that comes two ways. So first off, it can't be common. So there have been some really fantastic surveys done with Arecibo that have looked at either the entire Arecibo sky or swaths of the Arecibo sky, depending on which survey you look at, to pretty good depths. And they didn't find anything like this. Now, the Arecibo sky is limited. It's only, I think, alfalfa might be about 25 to 30 degrees in declination across the sky. So it's not covering everything. But if these things were common, they would have found them, clearly. So we know enough to know that it's uncommon. It's got to be fairly rare. I'm pretty doubtful that it's unique. The universe just doesn't do that. So there's probably more of them out there, but certainly none's been found yet. So the only real way, the second part of this, the real way to answer this is to do a very deep survey of all the rest of the sky, the areas that Arecibo couldn't reach. And really, to be blunt, the GBT is the best telescope for that. It's got an incredibly sensitive beam. It has very, very low side lobes, so you don't have extra detections. And we've got a nice radio quiet region here, so we've got more of the frequency spectra available to us than most other telescopes do. The problem with it, though, is the GBT right now has only got a single beam on the sky. So we've got the L-band receiver, which is a very, very good receiver, very sensitive receiver. But if you really wanted to cover a large swath of the remaining sky with a survey with the GBT's L-band receiver, unfortunately, it's going to take, well, at least 10,000 hours, if not tens of thousands of hours, depending upon how deep you want to go. So, if the NSF wants to dedicate the GBT to me and pay all the GBT to do that, that would be awesome. We can totally do this. Assuming that that's not going to happen, though, we need a multi-pixel instrument. And I just want to put a quick plug in for the fact that there is such an instrument being built. It was actually being built for Arecibo. This is called Alpaca, and with Arecibo's very unfortunate demise, it's being retrofitted to go onto the GBT. It's a 40 beam phased array feed system being built by Brigham Young University and Cornell University. It looks like it could do an amazing job with this, but I should add to this, it's an exciting instrument, but it's only funded right now to go through lab tests. So it'll be fully tested on the lab and on the sky from the ground, but the funding is not in place yet to put it up onto the GBT, and so fingers crossed that down the road we will be able to find funding for this to get it up onto the telescope and do a survey and find a lot more of these things. All right, so what is next with this source? So the next steps, which are well underway now, are some deep optical imaging in multiple bands to look for this galaxy. I will say that we've actually done this imaging. I'm not going to show the results yet because it's still a little bit preliminary, but I can tell you enough to tell you that I've learned enough to tell you that we are confident that this is real. We were confident already, but now we're even more confident, and we still have not been able to find it optically. So we've been able to push the limits a little bit deeper and still have not seen signs of this object so far. So that publication is still to come. Watch your, email box these days for that, but it's exciting stuff, and we'll just keep pushing at that. Unfortunately, though, looking at other wavelengths outside of the neutral hydrogen and the optical is not very practical at this point. A regular low surface brightness galaxy is typically pretty difficult, lots of telescope time to observe at other wavelengths, and now we're really pushing the surface brightness limits. We're clearly pushing the limits in terms of the diffuseness for these objects, and so it would just take a huge amount of telescope time with an unknown detection probability. So right now we're really going to push on the optical side as deep as we can, and we're going to, of course, go back to some of our array telescopes, notably the VLA in the fall when it switches over to D-array, to try to get more time on this and understand what we can with it. And then once we can finally detect it, hopefully we can detect it someday, we'll start looking to see if it's even feasible to look at other wavelengths. And then, like I already said, the other big thing to do with this object is to go search for more. So even though we only have one beam on the sky, the GBT is still a fantastic instrument for this. I've put in a proposal for this round to try to just start expanding our search out in this region alone. And so we'll do what we can with the instruments we have, and hopefully we'll start to see if somebody can find more of these objects, and we can start to try to understand a little bit about their environment and a little bit more about them. And so with that, I'll just put my summary up on the screen and take any questions. Thank you.
Thank you very much for a quite interesting presentation. We have some questions, and let me remind everyone to submit them through the Q&A button on the bottom. And we have one here. What is the physical dimension of the DSS image at the distance of the galaxy?
Jeepers. Well, I can show you the image, and this particular image on the sky is, so that's what, 9 points, that's about 10 arc minutes, so that's about 60 arc minutes. Yeah, this is a 60 arc minute by 60 arc minute image that you're looking at right now on the sky. We have searched out even farther, frankly, in other directions looking for it. So that's a 1 degree by 1 degree image, and the galaxy is at about 5,800 kilometers per second. So that's where we're looking right now, and there's just there's nothing visible there. Through the fantastic mosaicing tool you can do with SDSS, I've been able to look out to think I did a full 2 degree by 2 degree square searching for anything in the area and just couldn't find anything.
And we have another question. Would the size of the extended H1 emission detected by the GBT be consistent with cosmic web filaments feeding gas to the galaxy?
That would be awesome. That would be cool. It could be, but since we really can't say anything about the filaments, we can't say anything about the extent of the galaxy yet. I don't know, and that's where really a telescope like the VLA needs to step in. And I'm focusing on the VLA Meerkat. Unfortunately, I can't see this part of the sky. So the VLA can really help us with that to let us know if we really do have a broad extent of gas, and if we do, what it looks like, because there's no way to tell from a single dish telescope what the, like I said, we're struggling to even know the extent of this, and we certainly can't say anything about whether or not there's filamentary structure feeding into this or not. If you look at the neutral hydrogen profiles, you don't see anything that indicates a streamer. But again, the beam size is quite large compared to what you would expect for that. So it might be extended, and we're picking up some of the central gas there, where it might not be extended at all. So that would be awesome if that were the case, but unfortunately, I can't answer yes or no yet.
There's another question. This is a very big line width. Any indication of rotation or different velocities from the different pointings?
No, there's a slight difference here you can see on the screen. It is a big velocity width, but again, it goes down to the 9.8 arc-minute size of the GBT beam. That if this is extended, then you could argue that we are seeing a little bit of a rotation curve here. And certainly the galaxy is rotating. If it weren't rotating, you wouldn't have 150 kilometers per second velocity width. But we can't really read anything again from the GBT results so far. So the GBT did its job and got us the detection, but unfortunately is not going to be able to tell us those details. We really need a synthesis telescope for that.
3 questions, all asking the same question. Any hint of molecules, any CO data toward your galaxy? Is the H1 emission bright enough that one might try to detect OH?
We have not tried for CO yet, and the reason we have not tried for CO yet is because it's until we can really understand the extent of the hydrogen gas in this galaxy, it's not going to be worth trying to put in a CO proposal. Additionally, unfortunately, probably the best CO instrument we have is actually on the GBT, Argus, for these incredibly sensitive observations. And so my thought had been that we would use the Argus instrument to look for CO J1 to 0 on this object. We could just sum all the beams up on the sky into one area. First off, you got to kind of know where your source is to get away with that. But secondly, the diffuseness of the gas is making this very challenging. So remember, going back to those low surface brightness galaxy plots, the neutral hydrogen gas to CO gas ratios, I'm saying it the wrong way. The CO gas to neutral hydrogen gas ratios are quite low. In other words, the amount of CO gas compared to neutral hydrogen gas is lower than for a typical spiral galaxy already for most low surface brightness galaxies. And so unfortunately, the result of that is that it's going to take many, many hours of telescope time, many tens of hours of telescope time to detect CO gas in this. And so before we go try, which I do want to try, we really need to understand the H1 distribution so that we can point the telescopes at exactly the right spots. So that's down the road, but unfortunately a ways down the road. We need to get the synthesis data, synthesis image of the H1 to try and understand what the column densities are, turn that into what we expect to get for CO if it's normal spiral or low surface brightness, and then we will go off and look for CO. The OH question, OH is yet to be detected in any low surface brightness galaxy, even the much brighter ones, and so I don't think that, it has been tried for this certainly, but I'm not sure that there would be a particularly high success rate.
Another question. Have you considered where this might fall on the baryonic Tully-Fisher relation?
I have, but unfortunately I need to know more about the optical image, or at least get a better limit on it before I can look at that. But it's not going to sit on it. I'll say that I can say that quite confidently. If it were to sit on there, we would have seen the galaxy by now. So it's going to fall off of it, but exactly how far it falls off is unknown. And low surface brightness, the lower mass ones tend to fall off. There's lots of papers and been around for a couple decades talking about that. But this one could be a pretty interesting game of where it sits on that whole distribution. Remember too, in order to do a proper baryonic Tully-Fisher relation, I have to know the inclination of the galaxy to do any kind of inclination correction, and I don't have that yet either. But I would be very surprised if it sat even within the wider scatter of a typical low surface brightness galaxy on that. And that's going to be fun. Once we can do that calculation, it's going to be fun to see.
Well, we're coming near the end of our session, and we have many more questions pending. And Karen will send you the list of the questions so that you can answer them directly with the questioner. But let me summarize one final one. Has these observations been confirmed with another radio telescope? You have the detection of H1.
Not with another radio telescope, no, because there is unfortunately no other radio telescope with a clean enough beam and with RFI-wise and everything else to detect this. We have not been able to do this. However, we have gone looking with, like I said, with optical as well as in the H alpha. And we're getting some hints at H alpha for this, which is kind of an intriguing thought, because then you can ask why we're not seeing stars, and I don't really want to get there, so we haven't finished analyzing the data. But again, it reconfirms my confidence with this. And I should add that the observations taken with the GBT on this, for reasons called me being a director for the GBT for a while and a few other things, were taken with completely different instruments. So the initial data was taken with completely different back end set of data reduction than the more recent data, and it's all holding together quite nicely. So our confidence is very, very high on this.
Thank you very much. I'm sorry, but we're out of time now. There are still many, many questions that are unresolved on this fascinating object. Let me remind everyone that this has been recorded and will be available for your viewing in another day or so through the Green Bank Observatory website. Please join us in 2 weeks on May 8th, when Jack Orlowski-Scherer will present some results on galaxy clusters from Mustang 2, point sources in galaxy clusters, and other results from Mustang 2. Please join us then. Thank you and goodbye.